A warm welcome to all the viewers for the course Strength of Material, AME 302. Myself Thiapal, Assistant Professor of Department of Mechanical Engineering, JIS College of Engineering, is going to give a lecture on Module 1 on which we are going to discuss about elongation of the bar. So probably this is the part 2 lecture for elongation of the bar, because in the first lecture I have already told you what is the elongation in length for a circular bar if you are applying the load through axially, that is the coaxial load if it is applied, and we have also calculated the elongation in length for tapered section bar, and there also we have implemented the coaxial pull which have been considered as P load. So as you know that in this particular lecture we are going to cover up for the elongation of the bar. It basically means that when you are implementing load, then what is the change that is occurring in the bar. And the most important thing is that whether the bar is in horizontal position or it is in vertical position, that also we have to see. Now today we are going to discuss, or even you can say today we are going to cover up the topic that is the elongation of the bar due to its own weight. So whenever any bar is hanging freely, so the bar has initially got some weight, and due to this particular weight, what is the elongation in the bar, that we are going to discuss, or we are going to calculate in what way the elongation of the bar is basically occurring. So elongation of the bar, what thing that we have to consider before calculating, that is the initial weight of the bar. We have to consider what type of material that we are using for the bar, whether the bar is made up of same material or whether the bar is made up of different material, that is a composite material. It can be made up of 2 or more material also. For various material, only there will be change in the parameter for modulus of elasticity or Young's modulus, because the value for E, that is the modulus of rigidity, modulus of elasticity, or you can say the modulus of elongation, these are Young's modulus, it's getting varied for different material. So before we proceed with the lecture, let's have a look at the content. So as I have already told that we have already covered up in the first lecture of elongation of bar, that is the change in length due to axial load. We have also completed the elongation of a taper rod under the action of coaxial pull, and now we are going to discuss for this particular lecture, that is elongation of a bar under its own weight and bar of varying section. So these two particular thing we are going to cover up, and in the third lecture for elongation of the bar we will be covering up the compound bar with the initial weight along with some numerical. So as we are talking that today we are going to talk about elongation of a bar under its own weight. So you can see that we are having a bar and it has been hanged and it has got its initial weight also. So what is the change in elongation for that particular bar? It will be observed or it will be calculated in this particular lecture. And bar of varying section, it means that not only there will be the change in material, but also there is some changes in the cross sectional area also. Maybe it is having various length, maybe it is having the various diameter, and maybe it is having various material. So from there you can see how it is getting calculated for change in length for that particular type of bar. Ultimate, we are going to calculate the elongation of the bar, and elongation of the bar is none other than your change in length, that is your del L. That is the final calculation we need to find out to get the desired output of our study. Now let's move to the next slide. So you can see in this next slide we are discussing about elongation of a bar under its own weight. So when we are talking about under its own weight, you can see that this is a bar and you can see a load has been given here. Load has been given, in fact not, it has got a certain weight and that has been coming, or it has been shown in this particular downward direction. This will be termed as your weight. Okay. And again the thing that we have considered, that is we have considered L as your original length of the bar. A, capital A has been considered as your area of cross section of the bar, and rho, that has been defined as density of the bar material. And as I have already told that the bar has got its own weight, which has been given or denoted by capital W. You can see this is your capital W, which is also written as area into length into density of that material of the bar into gravitational pull, that is your G. So weight or pull that is acting on the strip, it is denoted by, or you can say the total weight of the bar is basically given by W is equal to area into length into density into gravitational pull of that particular body. Now you have to consider, again you have to consider an elementary strip of very small thickness. You can see this is very small thickness which has been considered as dx, and the distance of this small strip is from this free end at a distance of x. So you can see at a distance of x you have to consider a strip of thickness dx, and then you have to find out what will be the change in length for your entire object of a length of L. So if I ask you that what is the weight or pull that is acting on the strip. So acting on the strip means this particular strip, you can see the small strip. In this particular strip, how much weight or pull is basically acting. So your formula is same. A of this particular body area, or the cross sectional area of the bar, into your distance which you have considered x for that particular elementary strip. So area into distance x into rho, that is the density, into g, that is the gravitational pull. So if I ask you what is the elementary elongation of the elementary strip, again I am talking the elongation for the elementary strip, because if you are able to calculate the elongation of the elementary strip of that particular bar material, it is very easy for all of us to calculate the entire value of the bar, because we need to just have an integration of that particular equation from length 0 to length L. Is that clear? Again I am repeating, if you need to calculate the elongation of a bar under its own weight, then what you need to do is that you have to consider a body, you have to consider an elementary strip, and you have to initially calculate the change in length or the elongation that is occurring for the elementary strip at a distance of x from its free end. And when it is completed, it is very easy for all of us to calculate for the entire one. So if you go with the entire one, then you can see that nothing we have to do is that, only we have to integrate the above equation with respect to 0 to your length L. So initially I am telling that we need to calculate the elementary of the elongation of the elementary strip. So we are calculating the elongation of elementary strip, which is denoted by del L1, and again the formula is P into L by A into E. Again I am writing the formula. What is the change in length? That is P into L by A into E. So this P into L by A into E, the P, it has been given to you, that is the load. Load for which section? For this particular strip. So area into X into rho into G, if you put area into X into rho into G into your length L. So L length means the length of the elementary strip, that has been already considered as dx. So you are using dx here by area into your modulus of elasticity, that is area into modulus of elasticity, that has been mentioned here, area into modulus of elasticity. So this area is what? Area of the cross sectional area of the bar. So if you solve this equation, you can see in the lower section A is also there, upper section is A is there. So just remove it or you omit it, it is getting removed. And then what is the remaining equation that you have achieved for change in length? That is X into rho into G into dx by your modulus of elasticity, that is your E. So X means the distance from its free end to the elementary strip. Rho is density of that particular material and G is your gravitational force of that particular material, and here you can see dx, that is the distance of the elementary strip that you have considered by your modulus of elasticity. So now if I ask you, what is the total elongation of the bar under its own weight? That means from this 0 to L, this is your complete what? From this 0 to this is your L, this is your complete length of the bar that you are using. So this is your complete length of the bar that you are considering, which has been considered as your L. So if you integrate the above equation, that is integrate the above equation from 0 to L, then you will get the value as rho into G by E, integrating 0 to L for X into dx. If you solve it, then what you are getting? Rho into G by E into x square by 2, and you are putting 0 and L as the 0 as your lower limit, L as your upper limit. So what you are saying, that 0 as your lower limit and L as your upper limit. Now just have a look at this particular equation when you are putting the value. So when you are calculating, you are getting rho into G by 2E into X is now what? It is L. So it is your L square. Okay. So what is the final equation you are getting? That is rho into G into L, rho into G into L into L by 2E if you break it. So rho into G into L, rho into G into L, it is also termed as your what? Rho into G into L is equal to W into or W by A. From where I have got? This is from here. You can be written as W by A, because you have already gone through this particular text, because W is equal to A into L into rho into G. So there you can write rho into G into L is equal to W by A. So here you are putting W by A. So if I ask you change in length, that is del L or elongation of the bar, it is none other than W into L by 2 into A into E. So you can see for various section you have observed various equation of elongation of the bar. Everything is not same for every concept. It is clear to you, I think. So if it is clear to you, then I can say that for elongation of the bar, just normally, then I have told del L is equal to P into L by A into E. But for taper, you have got something different. And for elongation of bar for under its own weight, if you have gone through the content, then you have got something different value. That is del L is equal to W into L by 2 into A into E. So in every aspect, in every situation, everything is totally different, because this is basically not same. So change in length is none other than W into L by 2 into A into E, whereas for elongation of the bar, that is P into L by A into E. There you are using the load, here you are using the weight. So when you are using weight, the equation has been changed or deformed into del L is equal to P into L by 2 into A into E. So this is the basic concept of calculating elongation of a bar under its own weight. Now let's have a look at the numerical. So in this numerical, you can see the question that has been given to you: a bar of 3 centimeter square, that is area 3 centimeter square, of length 20 meter long and fastened at its upper end, and it has been hanged vertically under the action of its own weight. So if the density of the bar material is considered to be as 7.6 gram per centimeter square and modulus of elasticity has been considered as 200 kilonewton per millimeter square, then kindly determine what? It has been told that the extension of this particular bar or total elongation of the particular bar. So initially, if I discuss about this particular thing, you can see that required extension of a unit length, I am considering the unit length as A. Under the length, if you measure from, then you can see the change in length initially is L minus A, and you are considering the weight also. So x into W into dx by E, and if you solve it, then you will get the value for W by 2E. In bracket you are writing 2 into LA minus A square, that is very commonly known as W into A by 2E, in bracket 2 into length minus A. So if you have a look for the total extension, then total extension is given by, that is the del L dash, and you can see for this entire bar the concept is same, that is you have to consider a length that is from 0 to your upper limit L, that is the total distance. Now if you have a look in this total extension that has been calculated here, it is very easily it has been shown to you, that is W into x into dx, that is the distance of that particular elementary strip, and it has been told that you are calculating the weight along with the distance you have considered of the elementary strip at a distance of x, and by your modulus of elasticity, and when you are integrating from 0 to L, it is same way W by E is equal to 0 to L, which is also integrating which portion, x into dx, and finally you have got the answer W into L square by 2 into E. Now how you are going to solve it, it has been already provided here. So this is your W into L square by 2 into E. So this is your object, this is the strip, this is particular is the strip which has been considered as dx, at a distance of x from its free end, and total length of the bar has been considered as small l. Now next portion we are discussing about bar of varying section. Bar of varying section means that till this much time whatever discussion we have made, we have considered the length same, we have considered the area of the cross section of the bar as the same, and we have considered the material also same. But today in this bar of varying section, we are going to discuss about various portion of the thing. You can see three different composite bar, you can see number 1, number 2 or number 3, and you can see this bar are attached together, and this has been considered as one material. Here one thing is interesting, that is the material that have been selected for this entire bar is same. That's why your Young modulus of the material of the bar has been considered as only E. If it is a various material, then the value for E will be also changed. That is E1 for bar 1, E2 for bar 2, E3 for bar 3. But since you have got all the value for modulus of elasticity same, that's why there is no change in particular of this particular portion. So if you have a look of this particular bar of various section, then you can see that A, B, C, D, these are the three parts. Part 1, you can see that already there is length considered to be L1 for part 1. L2, it is the length of the part 2. L3, it is the length of the part 3. And if you have considered the area A1, A2, A3, then you can see various A1, A2, A3. You have got three different area also. And obviously you have to get that three different area in this particular manner, because area of the cross section 1 has got different length, it has got different diameter. So you have to get the value for area of the part 1 is different. Similarly, if I discuss about part B, then I must say that is area of the part B will be also different, because you have got different cross sectional view, that is length is something different, that is L2, as well as the diameter of the object has also you have received different. And if I consider area of A3, then there also same thing, because the length has been varied, that is your L3, and the diameter is also getting varied, that is D3. So in this way, with the help of diameter D1, D2 and D3, already the area has been calculated in advance. Now if I ask you that the total elongation of this particular bar, what will be the total elongation of this particular bar, then I must say that in this particular bar 1 you will have different elongation, in this bar 2 you will have different elongation, and in this bar you will have different elongation. So if you look at this particular figure in overall concept, then the total elongation will be represented by del L, which is none other than the sum of del L1, del L2 and del L3. So you can say these are the three change in length or elongation in the length for different section of this particular bar, and all this elongation together sum up will help us to get the total elongation of this particular bar. So if I ask you that if the modulus of elasticity of the material is same, then all these three bar will be considering the value for E same. But if it is of various material, like for bar 1 you have received the material as X, for bar 2 you have received the material as Y, and for bar 3 if you have received the material as Z, then you are going to get three different value for modulus of elasticity. So what I was telling, that is for different bar you are getting different modulus of elasticity, as well as for different material you are getting different property of that material. So it is helping you to get various modulus of elasticity. It doesn't matter because you are going to calculate the change in length or the modulus or the elongation length for different material in different position. So del L1 is equal to, in that particular case it will be P into L1 by A into E1. In fact area is also different. So P into L1 by A into E1. If you are using for calculating the second elongation of the bar, that is P into L2 by A into E2. Again for this del L3 you are getting P into L3 by A into E3. So you can see that in this particular situation your elongation material is same, that where your modulus of elasticity is same, that's why here it has been written EEE. But if it is of different material, then you have to calculate this particular portion in different sense or in different aspect. Now since the load here it has been given, that is your tensile load. You can see this is a tensile load has been given to you. Since the load has been given tensile, so it doesn't matter, the entire calculation will be positive because your elongation is occurring. The elongation is occurring because the load is tensile. But if it is having a compressive load, then in that particular case the elongation length will be decreased. It will be not getting increased because compressive load tendency is to decrease the length and to increase the diameter. So your area will be getting increased, but your elongation length it will be getting decreased because it is getting compressed. So your length, if it is of 100 millimeter and if you are using a compressive load, it can be reduced to 98 millimeter also. It can be reduced to 96 millimeter. That means your elongation in length will be 4 millimeter or 2 millimeter. But if you go with the elongation of the bar of various section with implementing a tensile load, if you are having a length of 100 millimeter, it will be increased to 108 millimeter. That means your change in elongation is 8 millimeter. It can be 120 millimeter if the load is too high. That means your elongation length is equal to 20 millimeter. So this is the most important thing that is basically occurring on this particular era. So now let's have a look with the example. So before we go with that example, you can see one more thing, that is if you put the value of del L1, del L2 and del L3 in equation 1, you can get the stress in the bar. Now what is the stress in the bar? That is none other than P by A. I have already told you that stress is what? You are implementing load over a particular area of the given bar or given section. So here also in the same thing we are studying here, and here you can see that the stress that has been introduced in the bar AB, that is the portion 1, is given by F1 is equal to, it can be written as sigma 1 also, here you can write as sigma 1 also, that is P by A1. You can also use stress in the bar for BC, that is the portion 2. It is also given by F2, that is also denoted by sigma 2, that is equal to P by A2. And stress in the bar that has been told as CD, it is in the portion 3, it is also given by F3, that is P by A into 3. So it is evident that F1 is minimum and F3 is maximum. Why F1 is minimum? Because the bar that has been attached towards the fixed position, you are going to have minimum stress there, and maximum stress is occurring at the free end because it is free and it has got initially the weight of the entire bar and it is getting hanged. That's why it is getting elongated due to this particular portion, because it is carrying the entire weight of the 3 bar. So the stress obtained is maximum. And if I talk about the section 1, there you are getting the minimum stress, because only a small portion it is having the weight, and its weight has been shared with the next second portion as well as third portion. So the stress that is obtained in part 1 is minimum, and the stress obtained in part 3 it is maximum. From this particular portion you can able to understand it. Okay. So just have a look at the numerical. It has been told a wrought iron bar is of 7.5 meter long and 5 centimeter is the diameter. If you look from the free end of 1.5, so this 1.5 distance is having a diameter of 5 centimeter. Next 2 centimeter is having a diameter of 4 centimeter dia, and next 4 meter length it is having 3 centimeter dia. So you can see this is section 1, this is section 2, and this is your section 3, and the load has been given here P here, and here it has been given load P here. So now it has been told you to, what it has been told you, that is the bar is in tension. So the elongation is occurring there. Tension bar means it is having an elongation, and it has been asked you find the total elongation of the bar, and the material is same. The material is same, which is having a modulus of elasticity of having 200 kilonewton per millimeter square. So initially what you are doing, you have to find out the cross section area of the bar, but you are not aware of the load. You need to know what is the aware of the particular load. So first you have to calculate, you consider the portion 3, this one. So portion 3, if you consider, you have got the diameter as 3 centimeter. So if I ask you to calculate the area of this particular strip, then it is very easy. It is pi by 4 into d square, that means pi by 4 into this 30 millimeter square. So there you have got the area. And the most thing is that you can see that the stress is in the smallest section. The smallest section stress has been given to you, that is 84 Newton per millimeter square. So if I talk about stress is what? Stress is equal to P by A. It is equal to P by A. So if stress is equal to P by A, that means P value has been not given here, so you need to find out, but stress value has been given here, that is 84, and what thing you have to do is that area value you have already calculated, that is pi by 4 into 30 square. So ultimately you get the value for P as 59376.24 kilonewton. So you have received the value for P here. So finally we came to the end of this particular lecture for elongation of the bar, where I have already discussed with you that how basically you are going to calculate the elongation of the bar with the initial weight, that is of the initial weight of the bar. And then we have discussed that if it is associated with a various section, then how you are going to calculate it. So you have noticed in the first lecture also of elongation of the bar, and in second lecture of elongation of the bar, that is in every aspect the change in length formula is varying. Because initially when we have studied about the elongation of the bar by implementing coaxial load, then you have seen the change in length is calculated in very easy manner, that is load into L, that is the length, by area into modulus of elasticity. Same thing, we are implementing the same concept, but we are getting some different calculation. That is, for this taper you have got 4 into P into L by pi into E into capital D into small d. So you have seen the various difference in the calculation for taper also. Next we have decided to calculate the elongation in length for using the weight. that is the initial weight of that particular bar. So in that particular situation also you have got some different concept, you have got some different view how it is calculated. And finally when we came of the various section, then there also we have seen that though the change in length is equal to P into L by A into E, but this value can be get different because the length is different, you are obtaining the area is different, you are obtaining the modulus of elasticity for various metal as different, so your entire calculation is also totally different. So here I conclude for today's lecture. If you have liked my video, then please like it, subscribe the channel and stay connected with me, so that in the next lecture we are going to discuss about the composite bar. We are going to discuss the same bar which is having various type of load that has been considered in one type of bar. That can be load can be compressive, the load can be tensile. So please stay connected with me so that you can have a great concept how to calculate the elongation of the bar in such condition. Thank you viewers for watching the video.